So we're going to do an example that involves finding the interval of convergence of a power series where the series is a little bit more complicated than the one we did in the first example. We can see a couple of complications here. First of all, we can see that the center is not zero. Instead of having ascending powers of x, we have ascending powers of x minus 5 in the series, so it's going to have a center of 5. We also see that there are some negative numbers in the series, and also that the denominator involves both an exponential function and just an ordinary power function, and the first. Also, I've started this series at n equals 1, and the reason for that is that if I started at n equals 0, I would get a denominator of 0. So you can't do that. What that just means is that we presume that the n equals 0 term in this particular series is just 0, but this definition, this general definition, couldn't be used for that term. It's not going to matter because, of course, the convergence or divergence of a series is determined what happens more closer to infinity than 0. So the fact that it starts at 1 is of no real consequence. So in any event, what we're going to do is we're going to start with the ratio test, like we usually do. We're going to calculate the limit as n approaches infinity of, I'm going to take this general term, but every place I see an n, I'm going to replace it with n plus 1. So that's going to be negative 1 to the n plus 1, x minus 5 to the n plus 1, over 4 to the n plus 1 times n plus 1. And then I'm going to multiply it by the reciprocal of the n term. That's how we use the ratio test. So this is going to be 4 to the n times n over negative 1 to the n x minus 5 to the n. And we want to do, oops, there we go. What we want to do is simplify this a bit. So this is going to be the limit as n approaches infinity of, I'm going to put the, first of all, let me just combine like terms, and I'm going to say, the first one I want to do is the negative 1 terms. If I take negative 1 to the n plus 1 and divide it by negative 1 to the n, I just get negative 1. Which means that if I left it in here, everything inside the absolute value is going to get multiplied by negative 1. But we know that that's not going to make any difference because the absolute value is just going to take the negative 1 and turn it positive. So I can take the negative 1 to the n term out. And that's something that in general you can do when you see an alternating term and evaluate it through the ratio test. So let's focus on the other terms. I want to put things that are similar to each other near each other. So that's going to be 4 to the n over 4 to the n plus 1 times, this is going to be, let's put the, so sorry, let me circle what I'm taking care of. Now I'm going to take care of the n plus 1 and n terms. So that's going to be n over n plus 1. And then finally the x minus 5 terms. So that's going to be x minus 5 to the n plus 1 over x minus 5. And if we simplify this a little bit more, we get limit as n approaches infinity of 1/4 times n over n plus 1. 1/4, 4 to the n over 4 to the n plus 1 is just going to be 1/4. N over n plus 1 doesn't simplify yet. We are going to be able to take its limit, but we can't simplify it yet. And then finally, x minus 5 to the n plus 1 over x minus 5 to the n. Sorry, I'd forgotten to write this n. I just wrote it in. That's going to be just x minus 5. We're left with 1 power of x minus 5. So this, observe that this limit is just going to approach 1. You should be able to do that with calculus 1 skills. If I take the limit as n approaches infinity of n over n plus 1. So this is going to be 1/4 times 1 times x minus 5, or just x minus 5 over 4. So this is the ratio test limit. As we know, what we want to do is set that limit so that it's equal to, so that it's less than 1, because that's where we're going to get convergence. So we set up this inequality and say that that limit is less than 1. That gives us x minus 5, absolute value of x minus 5 is less than 4. Now, there are a couple of different ways that you can now observe what the radius of convergence is. The first one is, just go back to your algebra skills. If I had asked you to graph the inequality x minus 5 is less than 4, you would have said, okay, 5 is the center, and this is all the points that are less than a distance 4 away from that number 5. So you'd go 4 in that direction, 4 in this direction, and you'd basically get a graph that looks like that. And it's just all the points that are between the interval 1 to 9. This, of course, is consistent with what we know about how radius of convergence works. We put the center at the middle of the interval, and it goes a distance of 1 radius in either direction. And we can see is that the radius of convergence is therefore going to be 4. That's how far we go from the center of the interval. The other thing to note is that if I get down to an expression that's just absolute x minus center is less than some number, then that number is going to be the radius. Which, these are really just sort of different ways of making the same observation. But this is what you're looking for. You're looking to get an expression that looks like this, like x minus center is less than some number, and then that number gives you the radius. So here's what we know at this point. We know is that the radius of convergence is 4, and the interval of convergence is at least, not negative, is at least 1, 9. When I say at least, what I mean is that we don't know yet whether it's a little bit larger. It might include one or both of these endpoints. We just don't know at this point. So that's why the next thing we're going to have to do is test the endpoints. So let's go to the next phase of the problem and test the endpoints. First endpoint to test is x equals 9. What we want to do is, if we go back to the original definition of the function, I'm simply going to replace this x with 9. So this is going to be the sum from n equals 1 to infinity of negative 1 to the n over 4 to the n times 9 minus 5 to the n. All I did was I took this series and replaced the x with a 9. Now notice what I did here. I turned this into a specific infinite series instead of a power series. There's no longer an x there. So I'm just going to be able to evaluate this. I'm going to, for convergence, using just the normal set of tools that I would have used to evaluate any series for convergence. This comes out to the sum from n equals 1 to infinity of negative 1 to the n over 4 to the n times 4 to the n. These are going to cancel, giving me the series negative 1 to the n over n. This converges because it's the alternating harmonic series. So, what we could have done is just observe that it's an alternating series and then test it with the alternating series test, but we did that for this exact series in the previous section. We observed that that was a special series called the alternating harmonic series, and we can just use that fact, and that can be used as a reason why this series converges. So what that means is that at the endpoint x equals 9, this series, once we get rid of that x and just replace it with 9, it just becomes the alternating harmonic series, like that. So now let's test at the endpoint x equals 1. So this is going to be the sum from n equals 1 to infinity of negative 1 to the n over 4 to the n times 1 minus 5 to the n. This time I replace the x with 1. So if I simplify this, I get negative 1 to the n times 1 minus 5 is negative 4, so that's negative 4 to the n over 4 to the n times n. If I simplify this a bit, I can combine all of these different things that are being raised to the n. So that's going to be negative 1 times negative 4 divided by 4. In other words, that just becomes negative 1 times negative 4 is 4, and then I have a 4, and those are all being raised to the n power. So I'm just taking all of these and just combining them using a law of exponents that you all would have learned in algebra or pre-calc. And then this is going to be times 1 over n. So this now becomes the sum from n equals 1 to infinity. That 4 over 4 is just 1. 1 to the n is just like 1. So this just becomes 1 over n. This is the harmonic series or just a p-series with p equals 1, so it diverges. So we've seen is that at this endpoint, the series just becomes a divergent p-series. So the interval of convergence does include that endpoint, but not that one. We conclude that the interval of convergence is 1, 9, like that, excluding the 1 but including the 9. Oh, I can't get the whole thing in. I can, as long as we make it really small. There we go.